All right, so now that we've defined the boundary operator, or the boundary map, it's like we're ready to introduce two classes of special chains, if you will. It's like which will then help us, characterize what it means for a chain to describe a whole. It's like in some sort of simplicial complex, for example. So this is the topic of cycles and boundaries. Okay, so we want to study sort of two sort of particular types of chains. Okay, so the first one, what are called P cycles. So, so this is a P chain with an empty boundary. Okay, so this is denoted by, well, the set of these are denoted by ZP. Okay, and this is of course nothing more than the kernel of the P boundary operator. Okay, and then you also have what are called P boundaries, which is a P chain that is the boundary of a P plus 1 chain. Okay, so that there is some P plus 1 chain whose boundary is that P chain, and if we have that property, then this is what is called a P boundary. Okay, so this is denoted by BP, maybe B for boundary, right? Okay, BP of K. And this is obviously the image, it's like of a boundary map, but it's not the p-dimensional boundary map, but the p plus 1 dimensional boundary map. Okay, so this is the image of boundary p plus 1. Okay, and then both of these things are groups. Okay, and then there's a fundamental result which basically says that which relates this, right? So it's easy to convince you. Well, I mean, it's like one has to check. It's like, but essentially what happens is that the boundary of something is going to vanish. Okay, and what that means that every boundary is a cycle, but not every cycle is the boundary. And in fact, it's like the that distinction is going to be critical to describing exactly this idea of wholes. Okay, so there's the fundamental lemma of homology. Okay, and what it says is that the boundary, the iterated boundary of any chain is equal to 0 for every integer p, so for every dimension, and for every p plus 1 chain D. Okay. All right, so let's try to show that. So again, I'm going to prove this in the context of Z mod 2Z. It's like coefficients, but it's not so difficult to prove this. It's like with integer coefficients. You just have to, again, worry about this issue of orientation. So let me just state the proof. It's like for Z mod 2Z, and then I'll sort of briefly explain what's different. It's like in more general sort of coefficients. So the proof is as follows, right? That it suffices to show this obviously for, that the boundary of a simplex vanishes, okay? And then because of the linearity of the boundary operator, right, it extends to this case as well. So suffices to show show this for a simplex as opposed to just a chain. Okay. So let's just say for a p plus 1 simplex, let's just call that tau. Okay, so the boundary, right, so the boundary of tau, right, consists obviously of p faces of tau, and then sort of every p minus 1 face of tau belongs to sort of exactly 2 p faces so the boundary of the boundary tau is equal to 0. Okay, so let me try to explain that, right? So what happens is that when you take the boundary, you just get the p faces, okay? And when you take the boundary of the p faces and you sum it all up together, you'll get all the p minus 1 faces, but they will have 2 of them when you do that, okay? And since 2 is congruent to 0 modulo 2, that means that the boundary of the boundary vanishes in Z mod 2Z arithmetic. Okay, so that's not so difficult to show. All right. So you might ask, well, again, it's like what happens if we're in this more general setting? It's like where instead of Z mod 2Z coefficients, you have integer coefficients, which is the usual setting for algebraic topology. And then there, essentially what happens is that, again, you have this property that the boundary of the boundary, it's like will involve sort of 2 terms. Well, the sort of every p minus 1 face will show up twice. It's like in the boundary of the boundary, but they will show up with different orientations. Okay, so if you recall, when you had integer coefficients, it's like there was this idea of the orientation or the ordering. It's like the simplices, you know, and so basically, well, maybe let's just sort of look at an example, right? So if you had something like this, right, with this orientation, right, the boundary of that are these edges, right? And then the boundary of the boundary obviously are the of a 2 simplex, which just corresponds to the vertices. But you know, it's like for each of these edges, so for this vertex, it's like it belongs obviously to these 2 edges, and then the boundary of this edge is going to contribute, it's like say a +1 to this, okay, and the boundary of this one is going to contribute a -1. So they're just going to have different orientations, and so those orientations will, you know, those different signs, if you will cancel things out, right? So, and again, you see this, you know, it's like in any calculation involving the boundary of the boundary, it's like of a simplex is that, you know, you will essentially have 2 terms, it's like associated with every p minus 1 face of that simplex. But, you know, it's like when you have orientation, it's like those orientations will have different signs, okay? And if you, if you, you know, it's like, you know, Z mod 2Z and you don't see orientation in some sense, then the fact that you just have 2, it's like causes that to vanish because of, you know, it's like 2 again being congruent to 0 mod 2, okay? All right, so in any case, it's like that proves that the boundary of the boundary of something vanishes, and that also implies that, you know, if you have a p boundary, it automatically is a p cycle, because what happens is that something being a p boundary means that it is the boundary of a p plus 1 chain. So maybe let's sort of write that down, right? So okay, so if, say, sigma p, I'm just going to denote that by the sigma here is going to tell me, it's like the p here is going to tell me the degree or the dimension, it's like of that simplex, right? So sigma p is in the boundary, sort of the set of boundaries, right? That implies that exists some dp plus 1, right, in the chain group, p plus 1 chain group, such that the boundary of dp plus 1 is equal to sigma p. All right. Now, okay, so the claim is that sort of sigma p being in the boundary implies that sigma p is in the set of cycles. And all I have to do is I have to apply the boundary operator to sigma p and see whether it vanishes. Okay. So this is just boundary, but sigma p is the boundary of d p plus 1. Okay, so that is just the boundary squared applied to dp plus 1, which by the fundamental lemma of homology vanishes. Okay, so that sort of proves what we need. Okay, so this means that every p boundary is also a p cycle. And more precisely, right, BP is a subgroup of ZP. Okay, and so we're going to, and because of the fact that there's this subgroup, it's like we can talk about quotient groups in a little bit. Okay, so and exactly this notion of the quotient group is going to give us what are called homology groups, which then encode something about holes in the complex. All right, so so let me just stop here for now.